everybody! In this video, I am going to show you how to make a calibration curve using refractive index. So this is a skill that you're going to need to have in organic chemistry to do the forensics lab. So let's go over some of the things that we need to do in order to get this done. Before we do that, let's look at some of the theory behind this. So, and you've seen this curve before probably in my other index of refraction video, but when you have a mixture of liquids, in this case we have a mixture of ethanol and water, it turns out that when you mix the two liquids, the index of refraction will fall between the refractive index of the two components. So ethanol's refractive index is somewhere around 1.36, water's somewhere around 1.33, and that means when you have a mixture of the two, the index of refraction will fall between those two values. And if you notice, the relationship between the two is mainly linear, and so because it's linear, we can actually make a calibration curve. Now, depending on the mixture, it will break down somewhere in the extremes. So we typically only plot data between 80% and 20% of the two solvents. So if we have water, we're probably going to go with between 20% water and 80% water. And this is good to know because I can guarantee whatever unknown you have, it will be between 80% and 20% solvent. It won't be at the extremes because then the calibration curve doesn't work. So what I've done is I have created a fake set of data. So normally you would go to the lab and you would make data that was like a solution that was 20% water, was 40% water, 60% water, and was 80% water, and then you would then take the index of refraction. Now I've kind of canned this data and I've kind of calculated it out so that it kind of just shows you what we needed to do, but nonetheless, you would go in and you would take at least 3 data points. I know that I would probably do more than 3, but 3 would be enough. So in this example, we're doing 4 data points, and I'm going to show you how to make a calibration curve using Google Sheets, but Excel will be the same. If you're using Excel, it would be the same process. Okay, so let me call up my spreadsheet. Here's our data. So we have, again, 20% water, 40% water, 60% water, 80% water, and then we've measured the refractive indexes using the refractometer in the lab. Now, in order to make a calibration curve in either Excel or Google Sheets, you highlight the data, if I can get it to highlight well here. Okay, so there's the data. Then I'm going to come over here, and I'm going to insert a chart. Okay, and notice it gives me a line chart right here to start off with. Regardless of whether you're using Google products or if you're using Excel, Microsoft products, you want to make sure that this is a scatter plot. So it's easy to change. You go down to scatter, and now we have this. Okay, so this appears to give us just a straight line, and that's it should be a straight line, but here's the problem. If you look at the y-axis here, it's causing our data to not be spread out and give us a true sense of the calibration curve. So what I'm going to do is I'm going to highlight this data here, and you notice this section comes up. Okay, now you'll see that we can do a min value. And so I'm just going to look at the data and I'm going to look and see what the minimum value is. And I see that it's somewhere around 1.3300. It's just above that. And then the max data, I'm actually okay with this being the max number 1.355. Okay, that's good. So now we have at least something that looks like a calibration curve. Okay. Now the next thing that we want to do is we want to see how good that calibration curve is by putting a line of best fit. So I'm double clicking on the graph, and then I'm going to customize this. When I go to customize, I can go to series, and under the series tab you'll see this trend line. So now what that's going to do, and you can see it pop up right here, is that there's a trend line that shows, and now using that trend line, I'm going to label it using the equation. Now that's important, okay, because you're going to use that equation to do something in your lab, okay? And so you also want to show the r squared value. That r squared value here, notice it says r squared equals 1. The best value that you can get is 1. Okay, think of it as a percentage on a test, except we're not doing the percentage, you're just doing the decimal equivalent of the percentage. If you have a 1, that means it's 100% accurate. The further away from 1 you get on the lower side, you can't have anything above 1. The further, the less accurate your line of best fit is. So that means that if you have something like a 0.95 r squared value, that's 95% good. And I think that in terms of what we're doing here for this lab, I think that if you have anything over like 0.92 or 0.93, you're probably doing a good job for your r squared value. And again, because I'm using predetermined numbers, then that's why my r squared value is 1. Okay. So now that we've created this curve, now Google's really nice because you can take this and you can copy and paste this into a lab report or something like that. But there's one more thing that you need to know how to do with your data, and that's going to be using this this equation of the best fit line. Notice it's in the form of y equals mx plus b. Okay. And that equation of the best fit line is going to give us the percent water that's in the graph. So let me show you how this works. What I have done is I've gone to the lab and I measured my unknown sample. Okay. So all of these percentages here were made by you. You went in and you made these samples so that you could knowingly create a calibration curve that fits the data that you can control. The thing you can't control is the unknown percentage of solvent in the water. So you go to the lab and you measure the index of refraction of your unknown solvent in water sample, and you get something like this. So this is what I did. I got 1.3453. Okay, so I'm going to put that here. 1.3453. Okay, so now with that information, of course, you can make some pretty good guesses here that it's somewhere between 40 and 60% water, but you want to know exactly what it is. Okay, so if you want to know exactly what it is, you're going to take this index of refraction from your sample and you are going to plug it into the math of this formula. And keep in mind that this is the y value here. Okay, so the way this is going to look is, and I'll pull up my my notebook so that you can see me do the math. And now I'm going to transfer that equation of the line of best fit, negative 2.52 times 10 to the minus 4 times x plus 1.36 equals y. Okay, so now going back to your data table, or not your data table, but your graph, keep in mind that the x value was the percent water, and your y value here is the index of refraction. Okay, so since we have an index of refraction that we just figured out from our unknown, which was 1.3453, so now we can solve this equation for x to get what the exact percentage of water is in our unknown sample. And so this is the expectation that I will have for you for determining what the percent water is by using index of refraction and using the calibration curve. You should both present the calibration curve and the calculations for how to determine, or the calculations on how you determine the index of refraction of your unknown based on the curve. Okay, so there it is, and have a great day, everybody.